Right, so let's have a go at Unified Chemistry, the final paper in the June 2017 series. Right, so this question is practice on reading the burettes. So I've written the answers below. Hopefully you could do this. Remember, you always record a burette read into two decimal places, and the final decimal place is either a 0 or a 5. So even for this one, for example, where it's 10, and you can quite clearly see that that is bang on the mark of 10, it's recorded as 10.00. So this is the way you do it. Remember, you would have done this as your practical final, followed by initial burette reading. Then you work out your titer. Now, in terms of working out your mean titer, you can see that this one and this one were within 0.1 of each other, so you would not use that one. And the average of that one and that one is 22.50. Right, so funnily enough, they now want us to use that titration. So here we go. They told us that it is, first of all, a monobasic acid. So we work out the number of moles of sodium hydroxide that we've used from our titer. So I've done that here. Remember, the concentration they've said on the previous page is this 0.0840, times it by your titer, divided by 1,000, and you have used 1.89 times 10 to the minus 3 moles of sodium hydroxide. That is the same as the number of moles of acid, because it's a monobasic acid, but that was in 25 centimeters cubed. Originally, the acid was in 250, so you need to times it by 10, and then finally the molar mass is the mass of the acid you used divided by the number of moles, which gives you 132. Now you've got that, you need to find what R is. If you add up the molar mass of that part, it comes to 75, which leaves it as being 57 for the R group, which is C4H9. So it's told you that it contains 4 optical isomers. So it can't be a straight chain. So the way you can do it is, if you do that, you will then end up with one chiral center being there and the other chiral center being there. And obviously each chiral center gives you 2 optical isomers. You've got 2 chiral centers, which gives you a total of 4 optical isomers. Happy days. Okay, so back to this lovely molecule now, and it's reacting it first with magnesium. Don't let it freak you out. Think of it as ethanoic acid. How would that react? Well, you're reacting it with magnesium. To get that to work, you need 2 of them, because magnesium obviously has a 2 plus charge when over here. So you're going to need 2 of those acids to react with magnesium to give you the salt of magnesium. Let's just put the charge of magnesium there as well, Mg2 plus, and then you've got 2 of the counter ions there, and you also form hydrogen gas, and that's of course a redox reaction. Now for the next one, slightly more difficult. So I haven't completed this one yet, so you can see how it works. You've got an alcohol on this molecule, which is there, and you've got a carboxylic acid there. So it can form an internal ester. Or it can form an ester with another molecule of itself, is what I mean. So how can it do that? Well, I've drawn them over here, and now I'm going to start rubbing things out. So let's go for it. So I've got 2 of my molecules over on the left hand side. What I'm going to do is I'm going to rub out the H there and the OH there, and I'm going to rub out the OH there and the H there, and then basically I'm going to draw some new bonds on. Now it's going to look slightly odd, but here's one new bond, and there's the second new bond, like so. And that is your cyclic dimer. And you obviously also make 2 water molecules as well, and it's an esterification reaction. So basically, that alcohol reacts with that acid, and that acid reacts with that alcohol, like so. Right, so we nip into some transition metal chemistry briefly now. It's a neutral complex that can be compared from this weak acid, and it wants us to draw the ligand, the structure of the ligand. So it's chromium 3 plus. So obviously each of these ligands here has got a minus charge. If that's one of our ligands, it's got a minus charge. So you basically draw that. The nitrogen's got 3 bonds, so he's going to be happy. So it's going to be the oxygen, which is going to be minus. Typical tablet contains 200 micrograms of chromium. Calculate the mass in grams of the complex that you need. Okay, so this is quite straightforward, really. Not really, well, it's kind of like AS chemistry, isn't it? Nothing too scary. You find your moles of chromium, first of all, that you need, or you start with, which is 200 times 10 to the minus 6 to convert it into grams, divided by 52, which is the molar mass of chromium. That gives you the number of moles of chromium. Then for every one complex has got one chromium in, so that's the same as the number of moles of complex. Then just times it by the molar mass of the complex, which is probably the hardest thing to work out, easy to make a slip. And that gives you 1.61 times 10 to the minus 3 grams. Okay, on to lovely thiols. Now, they say thiols are foul spelling. They are horrific. I used to work with these guys. They are awful. Anyway, they're also weak acids, which is lovely. So first of all, they want the Ka expression for this. Obviously, it's going to be the H on the S, which is going to be lost. That's the acidic H. So that's Ka there. Not too bad. Then this is kind of like chemistry, kind of need to sort of like just think about how would it react with an alcohol, which is pretty much the same, but the O is replaced by S. Same group, isn't it, in the periodic table, so nothing too scary. You take your ethanoic acid here, react it with your thiol, and it gives you this lovely compound here, plus water, as you'd expect. Right, you've then got 2-methylbutene, 1-thiol. So, skeletal formula. First of all, draw your carbon 1, 2, 3, 4 carbons. Ends up with your thiol on the end. So that's your butane thiol. Then you put your double bond, that's going to be carbon number 1 here. So that's carbon number 2 here for your double bond there. And then finally, carbon number 3 has your methyl group coming off. Alright, so this is quite an interesting one to finish off with for this question. So propane 1,3-dithiol, which I've drawn, reacts with propanone. How is it going to do that? Well, if you think about it, it's going to have, each of these sulfurs is going to have a lone pair on him. And remember, you've got a delta plus carbon there and a delta minus carbon there. Now, we're not going to get into the nitty gritty, but basically you're going to lose the H from here. I'm going to get rid of those lone pairs as well. And here, I'll just put my S back, which I've so rudely deleted. And we're also going to lose the O as well. Now it says a condensation reaction, so I'm going to put those two molecules together, and then I'm going to draw my new bonds going from the sulfur to the carbon like so. Now it doesn't look pretty, I admit, but it's right, so it should get you the marks, and let's just get rid of that delta plus there as well. And obviously they want the equation, so your other product is going to be plus H2O. So you need to draw this out properly as an equation, but you get the point. Okay, so final question now. I've done a little bit of prep work. So I have labelled B, C, D, E, F and G with their functional groups. And it's really important that you work out which is a primary, secondary or tertiary alcohol. And we've got alkenes and so on. Now, think about these functional groups. How do you test for each of those? And then just make yourself a list. So alkene, we use bromine water. For primary alcohol or secondary alcohol, we can use potassium dichromate in acidified solution, which would go orange to green. 2,4-DMP is used to test for an aldehyde and a ketone. And finally, Tollens reagent is for an aldehyde. So before you do anything, the key thing is to write down the tests for each of these functional groups and then go through B, C, D, F and G and work out which will react with which. So let's go for bromine first of all, bromine water, which as we know, when it meets an alkene, goes orange to colourless. So it will go for orange to colourless with B, with C, with D, and also with G. How about potassium dichromate, acidified potassium dichromate? What about that one? Well, that will react with primary and secondary alcohols to oxidize them. So, what will that react with? Well, it won't react with B because that's a tertiary alcohol. It won't. Oh, it will react with an aldehyde to make a carboxylic acid, so it will react with C. It will also react with D because that is a primary alcohol. It won't react with a ketone because ketones can't be oxidized. F, it will react with a secondary alcohol to produce a ketone, so it will react with F. How about with G? No, it won't react with ketones. They can't be oxidized. 2,4-DMP. So 2,4-DMP will give you an orange precipitate when it meets a ketone or an aldehyde. So it will react with C. It will also react with E. It will also react with G. Okay. And finally, Tollens reagent. Tollens reacts with aldehydes. So Tollens reagent will only react with C. So let's go through how would we identify these? Well, B will only react with bromine water. C will react with all four. D will react with bromine water and potassium, acidified potassium dichromate. E will only react with 2,4-DMP. F will only react with potassium dichromate, acidified potassium dichromate. And G will react with bromine water and 2,4-DMP. So you can see when you look at your ticks, no compound has the same ticks for the same test, so that will allow you to identify your compounds.